Last time we looked into Postgres extensions for time series management, implementing anomaly detection based on weekly behavior, and we also explored extensions for vectors and AI, building a very simple recommender system that summarized 100 suggestions into a nice user overview. Today, for the fourth and final part of the PostgreSQL Maximalism series, we will look into extensions for full-text search, graph analytics, and message queues. Let's begin! So let's begin by looking at full-text search. For reference, we've got Apache Lucene, Elasticsearch, and Apache Solr. All of them are based on Lucene. For Postgres, we are looking into TS vector and TS query data types. Postgres also provides a generalized inverted index known as GIN, and it's got text preprocessing pipeline configurations that are usable by 2TS vector or 2TS query to preprocess a string of text. The English configuration, which is the default, usually tokenizes text by spaces and punctuation. It converts to lowercase, removes English stop words, and applies Porter stammer. So Postgres provides the TS rank and TS rank CD examples for ranking functions or scoring. They claim these are only examples and the user should implement their own ranking functions. Then we've got ParadeDB, PG Search, which was previously known as PG BM25, and so they brought BM25, which is a ranking function, into Postgres. The extension is quite large and takes quite a long time to compile, and it adds a ton of Lucene-like features. It's based on TanTV, which is a Rust-based Lucene alternative, so that's interesting. Then we've got PG Trigram. This is a built-in extension. It's based on character trigrams, not word trigrams, and it's useful for fuzzy search, so for string similarity. For example, let's say you have product names on your database and you want to match it in a fuzzy way so the user can make some spelling mistakes. You can use PG Trigram for this. It can also be optimized via the GIN or GIST indexes. Then we've got Fuzzy String Match, which is also a built-in extension. The interesting feature of this extension is that it helps you match similar sounding strings. Although it's interesting, we'll not be looking into it. And you also got a third-party extension called PG Similarity, which provides multiple text similarity functions, and it is supported by the GCP Cloud SQL and AWS RDS, so that's something to take into account. However, the last commit has been over 5 years ago, which doesn't really mean anything because text similarity functions don't change that much, and as long as they were properly implemented, I'm sure it still works quite well, although it has some forks that fix compilation issues for the latest versions of Postgres, so that's something to take into account. So now let's look into a bit of a demo. As usual, under SQL you'll find a folder for this search category. Let's begin by loading some data, so we'll create this doc table with an ID, some textual content, a rating, and a publish date. Let's copy this into pgcli as usual. And we just created the table. You can check it out. And as you can see, this table contains the ID, some text, a rating, and a publish date. So now let's look at built-in capabilities of Postgres for search. The first thing you need to do is to create an inverted index, and you can do that by running this create index using GIN. and then you convert a textual column into a TS vector. Usually you have to give it a configuration profile which corresponds to your pre-processing pipeline, and this will index your table. So let's create this index. You can check it whether it was created by looking at DI, and if you want more details you can add a plus for index size. Now let's do a simple query, and let's make sure we use English on our 2TS vector. If you don't use English, by default it will still be English, so you can call it like this. However, it will not match your index, and to create your index you need to provide the pre-processing pipeline name, your configuration name. You cannot create an index like this. Okay, so in here let's look at this query. We are selecting the ID and the textual content just for debugging purposes, and then we are converting this content into a vector as D, and then we are creating our query. We want to match any documents that contain Postgres or performance. This is the default when you search the web for Postgres performance. It would be an OR, and then it would rank your documents from the most relevant to the least relevant, which would mean that documents with both words would be on top. And so we are using TS rank, and you give it the document, the vector for the document, you give it the vector for the query, and you give it an optional normalization. This maps into one of several ways to normalize your ranking function. We can take a quick look at how this works. If we go into Postgres and we search for TS rank, in here you'll find the documentation. You've got the TS rank and TS rank CD, and you'll find there is an optional weight. There is the vector for your document, which we were passing on our example. There is the vector for your query, and then there is a normalization integer, and this normalization integer will do one of these things over here. We are using 1, which divides the rank by 1 plus the log of the document length. So this will always be some kind of normalization based on document length. Otherwise, long documents containing a keyword that would repeat over the document would rank higher, and they might not be as relevant as other documents that contain multiple keywords that you are using to match your query. And so let's go back into the terminal. Let's copy this over, and here we go. Just a detail that I left out. We are using the @@ queue to match a document with a query, and this will only filter documents. And then we are ordering in descending order by score, which is given by TS rank, and this is the score it computed, the document ID, and then the text. And you'll find that documents containing PostgreSQL and performance will be ranked higher. So we got PostgreSQL in all 3 documents, and let's try to find a performance string. For document 2 you can find it here, and for document 1 you'll find it here. These are the basics to work with full text search on Postgres. It's not that complex. However, we are quite limited based on the ranking functions they provide, and this is where PG search comes in. They started as an extension that provided BM25 as a ranking function, but they evolved into much more. they provide their own indexing strategy. They call it PM25 even for the index. And this index has a particularity. Instead of using Postgres configurations that we had to set up separately, we can just create our own configuration inline. So for instance, in here we are indexing the same data as before. We'll be indexing every field, so they will be available within the index to filter. We are giving it the key field as the ID, which is the field that it identifies the document uniquely. We are giving it text fields. In this case we only have content, and this will be the field for full text matching. And then we can define the tokenizer. In this case we are using bigrams and trigrams. We can also define the stemmer. We are still using an English configuration, but you could essentially just create a separate index for your separate languages. And then we can also define numeric fields, so they can be used on range queries. Let's create the index. Here we go. The index has been created and it is listed over here as usual. Then let's inspect the index, which is something that ParadeDB lets you do. So the index contains these fields. We already knew about this. It's got a CT ID as well, and it's got their internal field types. And we can also check the size of the index by running this query, which is standard Postgres. There you go. You can also do it by running di plus, and it will be shown over here. Now let's test some query types. So instead of the double at operator, it uses a triple at operator to distinguish from the default Postgres operator. So if we want to do some basic matching, it's quite similar to the strategy we used before. It's just less verbose, more user-friendly to write it this way. So this just matches documents that contain these terms, either of these terms, because I believe document number 3 does not contain the term performance. Let's just check it on VS Code very quickly. So if we go into here and filter by performance, you'll see that document number 2 is the one that does not contain performance. As you can see, when you run this query, it will match either of these terms. Then you can also use field matching, which is something that isn't available within the built-in Postgres extension for full text search. So let's test it out. And as you can see, we filtered by PostgreSQL for content, and rating must be equals to 5. And as you can see, we've got only one document with rating 5. No other documents were returned. So now let's add scoring. So just call the score function from the ParadeDB schema and pass it the ID. This is very similar to the previous query. We are only ranking the documents. And as we can see, the documents are now ranked. So it will match documents with these two terms, and will rank documents that contain the two terms higher. So this is what's happening here. Since document 2 does not contain the performance keyword, it will be last. Next, we have an example of range filtering, which is something that is also supported by ParadeDB. So in here we are combining a regular query and we are ranking the documents, but we are also filtering the rating from 3 to 5. this should only return 2 documents, I believe. And here we go. If we check the rating, it will be 3 and 5 explicitly, but it just means it's within the range. Then we have also set filtering and range filtering. For set filtering, we can use this in operator and give it values separated by a space. And for range filtering, in this case we are using dates, which is an interesting example. We can use it this way, so with the to operator. This is also inclusive. As we can see, now we only have one record, because 3, 4 and 5 would match the previous 2 documents, but the date does not match the other document because it was from 1999. We can check that out by going to the previous query. You can see it's from 1999, so it would never appear. Now we can also query based on using boosting, term boosting rather than field boosting. It's called term boosting. And I'm going to run the 2 examples, one without boosting and one with boosting. So boosting PostgreSQL to 10. And remember, this is the same as an OR. So let's copy this. As you can see, we'll get document 2, 1 and 3. Let's check the rating. So rating 5 is on top, and then we have the other 2 documents that also match. Now let's copy the one with boosting, where PostgreSQL has a weight of 10. And here we have document 1, 2 and 3 in order, just because 5 is not as relevant anymore and Postgres is weighted higher. And this is it for a simple overview of PG search. Let's get into PG trigram, just a short example. We've got term 1 that is programming, then we've got programming with a spelling error, there is a name missing and an additional word, and then want to measure the similarity between the 2 terms using similarity, word similarity, and using this matching operator to check whether they do match or not. So let's see what this outputs. And so we have our term 1 and term 2. The similarity is over 50%. The word similarity is much higher because it will compare each word pair, and it is a match. So if we used programming again with this spelling mistake, we could match this or vice versa. And this is something that is very simple, built into Postgres, that can be quite useful for everyday tasks as you are building a website and trying to match your product name to a string or a category or something like that, and don't need heavy duty full text search. You can just use this word similarity, which seems to work quite well for these tasks, or simply the boolean match operator. It will just return the words that best match. You don't need any ranking. And now let's go into graphs. Again, for reference, we've got a few examples outside of the Postgres universe. We got Neo4j, which is the state-of-the-art in graph database technology. We've got OrientDB, which is a multi-paradigm database which also supports graphs. And we got the most recent CusoDB, which is an embedded graph database, and it seems to be on the same level as DuckDB, but for graphs. We'll very soon export that database in the channel as well. For Postgres, we've got a few options, none of them particularly good. We've got PG routing, which is based on PostGIS, and it is extremely directed at geographical graph computation. So computing shortest paths or computing high pressure points on traffic networks. Then we've got Agents Graph, which is a fork, a Postgres fork by a South Korean company called Sky Worldwide. This one was fairly interesting, but it was outside of the scope of this video because we are looking at Postgres extensions, not forks. Then we've got Apache Age for a graph extension. In the beginning it felt promising, but they do not provide any relevant graph algorithms, at least at this time. It is fairly recent, although it already is 5 years old. We also looked into PG Graph, but this is an extremely limited package that only provides SQL implementations for Dijkstra and Kruskal. And it is a project that I deem dead on arrival. It has been abandoned for 9 years, so I wouldn't really consider this for any graph needs on Postgres. In fact, if you have graph needs, this is probably the only instance where you should look at specialized solutions outside of Postgres, at least for now, and probably look at Neo or Kuso. Let's look at PG routing and understand why it is as limited as it is. Again, let's go into our SQL folder and we'll find a graphs entry over here. First thing is to get some data into Postgres. For this we used an external graph loader, this graph load script over here. So the graph load script, we tested this with 2 data sets. We are downloading data sets, unzipping them, and then creating the tables over here and copying the data via copy. We are doing this because we are loading data from the Snap Stanford web page. They provide some very interesting real-world complex networks for you to test out, like Facebook network or Twitch gamer network. We provided both options because the Twitch graph was a bit too large for us to analyze on Postgres. This is why a specialized solution like Neo would be better suited for analyzing graphs. Maybe CusoDB, but I'll have to test it out still. And so we are going to use the Facebook dataset for this example. Let's load it out. So we can run this command, graph load. Let's load it into data. This works as a cache, so if the dataset has been downloaded already, it won't need to download it again. And this just created graph namespace. It only creates the graph nodes table and the graph edges table. You can actually select from graph nodes. Let's look at the first 100 nodes, and we've got a node ID, and then we've got some metadata for the node. You can also look at graph edges, and we've got the edge ID and the source and target IDs. Although we are treating this graph as undirected. And so we have loaded some data. We can run this query, which will give us a few stats. So it will count the number of nodes, it will count the number of edges, it will count the number of linked nodes, and we've got 22k nodes, all of them are a part of an edge, and we've got 171k edges. As you see, this is not a large scale graph by any means. We can usually still analyze about 1 million edges on a single machine without a problem. So let's look at what PG routing can do. So one thing PG routing provides is this PGR extract vertices function. It is useful for us to create a table with the output of this function, because since we are working on Postgres and we do not have specialized index or a specialized storage approach, the only way PG routing deals with efficiency for some computations is by creating tables with the required output. It's easier just to show you. So let's create this graph node info table. And what we've got here is a node ID with an array with the IDs of the incoming edges and an array with the IDs of the outgoing edges. So there is this property called index-free adjacency, and this somehow simulates that property, although we would still need to load the information for the node. We only have the edge, so we'll still need to query the edges table and then reach the node. This is a somewhat in between solution that lets some operations perform better. One of those operations is computing the degree of nodes. Let's just stop for a second with the graph extension demo and look just at a detail over here. So in Postgres you've got these double dollar signs that are used to quote strings. So this would be, let's say that we wanted to write a function, the same function as, and we should include the SQL over here, you know. So it would be something like begin, return, query, etc. Let's look at this particular example where we are calling the PGR degree over here with also quoted queries. So if we try to use just double dollar sign, it's as if the function would end here. And one thing Postgres provides is a way to name these string quotings using any string you want over here. So as long as you open this and close it in this way, this will be considered a string within this top level string, and the function will not end here but only here as expected. This is just a neat trick you can use with Postgres that I believe is not that well known. So now back into how to compute the degree for our nodes. We have this degree function, and you can give it a select with the edge IDs that you are considering, and also you give it the fields from the node info table that we computed previously using the extract vertices function. So we created this as a function just for demoing this, but in fact we are going to create a table called node degrees with all this information. So let's create this table and look at the node degrees in descending order. And there we go, we have a node with 709 edges, both ingoing and outgoing, because we are disregarding direction. We are treating this as an undirected graph. And now let's select two random nodes for us to compute the shortest paths. We're going to do this manually just so that we can follow along each step. So we have these two nodes with degree 7 and degree 3. Let's copy this node ID and paste it here, and because I'm using a seed, this is reproducible, and so the values are already set in here. This is what I'm doing by selecting set seed in this transaction. It must be done within the same transaction. Okay, we didn't have the begin and the end here and moved the select seed outside. This would be run on a separate transaction, and this set seed of 0.5 will not be considered. So it would be actually random every time. It would change every time. So in order for us to compute the shortest path using Dijkstra, we just pass it a query that outputs the edges and the cost of the edges. It is mandatory that we pass a cost, so we just use 1 for the cost. Then we pass the vertex ID for the start and end, and in this case we do not want to compute based on the directed version of the graph, so we are always working with the undirected version. Let's look at the output. We are starting at vertex 1963 and we want to reach vertex 17529. So this would be the shortest path. Remember, this is undirected, so sometimes the order might be switched. So we are going from this to this, and then from this to this, and then from this to this, and so forth. Okay. So one common task that we do on network analysis over complex networks, so real world networks like a social network, is test for a small world. And in order for us to test for a small world, we need to compute the average shortest path, and we also need to compute the clustering coefficient for the graph. So let's begin with the average shortest path, and we do this based on a sample. So what we do is, first we create this node sample table where we just select 5 nodes. Let's do that. We just created this node sample table. We got these node IDs. And now we can look at how many shortest paths it will compute for the 5 sources by doing a cross join. So this would be worst case scenario. We are doing 112k computations, and this is why we are scaling this down. Okay. And now we are going to use PGR cost, which will give us the distance between 2 nodes. And this is very similar to the previous run with Dijkstra, where we are required to include a cost, and we give it the query for the edges, and then a query based on our sampled nodes with all other nodes that we want to compute the shortest path to. This is undirected, so let's create this table. We can also inspect the table, and we've got the starting vertex index, the end vertex index, and the aggregated cost of reaching this vertex from this vertex. So this would be a 4 hop, a 6 hop, etc. We can also count how many distinct source nodes and target nodes we've got. We've got 5 source nodes, the ones that we sampled, and then 22k target nodes. So how many nodes in total do we have? We're just doing this to understand whether it is fairly representative or not. So in total we have 22k nodes, which means that these 5 nodes are a part of the 22k as well. And now let's go into the local clustering coefficient for each node. One way to compute this is to look at the number of edges between the neighbors of each node. So in order for us to support this computation, let's first create an index for source ID, target ID, node ID, and the tuple. Of course, query optimization is beyond the scope of this video, but I had to explain on some of these queries in order to make sure that they were hitting these indexes. So let's create our table with the edge count for the neighbors based on our sample nodes. So this first query essentially just fetches all the neighbors based on the undirected information that we have. So we first go into target ID and set it as a neighbor ID, and then we go into source ID and set it as a neighbor ID, and then we simply count for each node the number of neighbor edges. We join with the edges table based on the source ID and based on the target ID. Either one of these will lead to neighbors, and then we group by node ID. So let's look at the output of this. And as you can see, this took nearly 20 seconds to run. And so as the output, we'll get each of the 5 sample nodes and the number of edges connecting their neighbors. This is a very small sample, but you could essentially just scale this strategy and approximate as best as you can given your hardware if you are doing this on Postgres. And now that we have this information, we can compute the clustering coefficient. So the formula for the local clustering coefficient is just 2 times the number of neighbor edges divided by the degree times the degree minus 1. So this would be the maximum number of connected edges among neighbors, hence the degree minus 1. We are removing ourselves from the equations. So the node we are computing the local clustering coefficient for, and this is why we multiply by 2 over here. Just because this is an undirected graph, and we are, by computing this product, we are not considering direction, so this should also not consider direction by multiplying by 2. And so let's check out what is the output of these local clustering coefficients. And there we go, we have a local clustering coefficient for each of these 5 nodes. Again, the local clustering coefficient will not tell you much unless you compare it with a null model, and that's what we are going to do. So now we are going to decide, is this a small world or not? So the clustering coefficient for the graph is just the average of the local clustering coefficients for every node. We are just based on a sample of 5 here, which is not enough, but it's enough for demoing. And also the average path length is essentially just the aggregate cost from Dijkstra, the average over that aggregate cost. And then we compare it with some reference values. We are using 6 for the average shortest path length. If it's lower or equals to 6, then we consider it to be short average path length. This is based on the 6 degrees of separation, just as a reference. And then we compare the clustering coefficient based on this reference, which is computed from the Null model. The Null model is just a random graph with the same number of nodes and edges, but all the edges are randomly assigned between nodes. Then we compute the clustering coefficient over that graph and we use it as a reference. So if our graph has a lower shortest path length and a higher clustering coefficient than these reference values, it is considered a small world. And let me just show you how we computed this value. So first we are going to launch Jupyter Notebook. Let's first run all the imports. Let's jump into our graph section. In here we are creating a null model. So we just need to know how many nodes we have on our graph nodes, and we need to know how many edges as well, and we can compute that over here. And then we have the number, we use the number of nodes and the number of edges to compute a probability of linking any two nodes for our null model. And then we use Erdos-Renyi graph, which is a random graph generated with the number of nodes n and the probability of linking any two nodes. This will take about 16 seconds. And once we've got our null model, we can compute the average clustering coefficient. We are using network X, by the way, in here. We can compute the average clustering coefficient for this null model, and we'll get a very similar value as the one we got before, that we can actually use this one and copy it over. And so if we go in here and just replace this reference value with one that was computed, which is very similar, we can now run this query and check out whether our graph is or isn't a small world. And lo and behold, our graph is a small world, because we've got an average shortest path length of about 4. This is well known. The degrees of separation on Facebook are not 6 but 4. Is this a short path? Yes. We have a clustering coefficient of about 31%. And is this a high clustering coefficient? Certainly yes, it's much higher than the null model. And so this is a small world. This is just an example of how you can use Postgres to do regular network analysis. Although I feel like this is far from ideal for our current graph computation needs. We are not even touching into clustering algorithms, community detection, KCOR computation, node embedding. So in this aspect, Postgres is really lacking. And now we're going to go into message queues. As usual, we've got some reference examples outside of Postgres. You've got Redis, where you can use the queue or the PubSub API. You've got ZeroMQ, RabbitMQ, and Apache Kafka. And for cloud, you've got Amazon Simple Queue Service and Google Cloud PubSub. Now for Postgres, you've got PGMQ, which provides the create queue function as well as send and read functions, alongside other utilities that support the producer-consumer pattern. It integrates with over 10 languages via official and community libraries. You've got a Rust and Python official library. There is PGQ, which provides the create queue function as well as insert event and register consumer. You can also get batch events, and this supports the publish subscribe pattern. It was created by Skype in 2016. Finally, there is PG message queue, which provides a PGMQ create queue, send message, get message bin for bytes, or get message text for plain text, and it also supports the listen operator for synchronous notifications. This was originally published via an SVN repository and later migrated to Google Code. The code by the original creator is no longer available or maintained. While a fork exists on GitHub, the project seems to be abandoned. Then we've got our message queues based on libraries. For Python, we've got PGQer. PGQer relies on a sync PG instead of psycop G2, which is the standard library for accessing Postgres from Python. It can be configured with default Postgres environment variables, but there is no default envar to set the connection string, so you can set the envars individually. Queues are managed programmatically and via the command line interface, and only one queue exists per database, which is stored in the PGQer jobs table. Then you've got PGBoss, which is a JavaScript Node.js library that provides the PGBoss object, instantiated with a connection string this time. And this creates a PGBoss schema where the queues are named and managed. Finally, you've got several Ruby libraries. There is delayed job, which is a library extracted from Shopify. It supports active job and it is not specific to Postgres. It provides multiple features to handle diverse tasks at Shopify, and one of the features is named queues. It's not the best option for general purpose message queuing on top of Postgres. Then you've got Queue, which focuses on reliability and performance, taking advantage of Postgres advisory logs, which are application specific logs that can be set at session level or transaction level. These fail immediately when locked instead of blocking like row level logs do, so workers can try another job. Then you've got Good Job, another Ruby library inspired by delayed job and queue, and it also uses advisory logs but provides active job and Rails support as well. And finally you've got Queue Classic, which is a Ruby library specialized in concurrent locking and supporting multiple queues and workers that can handle any of those named queues. And now let's test out PGMQ. As usual, we have a directory dedicated to this message queue category, and we're going to run a very quick demo on this. So let's make sure we start from an empty state. Then let's create a message queue called requests, and it's done. Now let's check which queues we have on our system, and we can find the requests queue, which is not partitioned and not unlogged. It was created just now. Now let's drop this queue again, check that it's been dropped. Yep. And now let's create a partitioned queue, which is used for efficiency reasons. So this by default creates 10k size partitions, and this requires Partman to be installed. So let's also create an unlogged queue. This unlogged queue improves performance once again through a different strategy at the cost of safety. So by not writing to the write ahead log, the wall, we can use it when you can tolerate message loss but need high performance, and perhaps you don't have such a high volume of messages coming in like you would for partitioned queues. Let's check out what we have now. Now we have a partition queue, requests, and an unlogged queue for jobs. We can check that the tables for the unlogged queue are marked as unlocked with a U versus the regular ones which are marked with a P for permanent. And these queues are usually prefixed by queue underscore and the queue name. We are going to look at the tables for jobs and requests queues, and as we can see, the jobs one is marked as unlocked. Now let's go into operations to check which types of operations we can do with queues. So first of all, let's look at the pgmq send, which will send a message to the jobs queue. This message will be a JSON document with an action send newsletter and the user time zone set to UTC+1. We can use delays. This is optional. This will delay adding this message to the queue by 10 seconds. And in a real world scenario, we could, for instance, schedule this for the upcoming 6 p.m. and I can show you how this computation would work. So, and I'm using 1 p.m. over here just because it's over 2 p.m. where I'm at, and it's the 28th, and this would mean that the next 1 p.m. would be tomorrow, the 29th. If we switch this to 5 p.m., so 1700 hours, and you run it again, then it will be today at 5. So let's send this message. It will take 10 seconds to reach the queue. It's immediately completed, but it will only enter the queue in 10 seconds. And now let's read from the queue with poll, which means that we'll wait at most 15 seconds. VT is for visibility timeout, which means that when we get a message from the queue, it will be invisible in the queue for any other workers to retrieve, so they won't be able to see it for 30 seconds, and we can renew this value, or it will eventually expire, or we can delete the message completely. So should have been 10 seconds by now, and we do have the message that we sent over here. So if we read it again immediately after, you'll wait 15 seconds, and if nothing is there, and remember that it is a visibility timeout of 30 seconds, so after 15 seconds nothing should be there and it should come out empty. Okay, and if we wait a bit longer, we will be able to run this again and get the result back, as you can see, because this visibility timeout was not renewed. So for now, let's pop a message from the queue, which means we are going to read it and at the same time remove it from the queue. And let's also reset the whole queue. We can do it with purge queue. Another thing we can do is send a batch of messages. This is set as a Postgres array of JSON objects. Okay, so let's do that. We sent 2 messages. Now we can read these at most 5 messages from the queue. The visibility timeout will be 5 seconds. And we've got both messages over here. Now let's say that we want to set visibility timeout for message 2. If we go back and try to read, we only get message 1, at least for 5 seconds, and if we run again, then we got message 2 back. Then we can also archive a message. We've got message 1 and 2, let's archive message 2, and this will move it somewhere else in a scenario where you need to keep history available for future debugging or accountability. This is how you will delete a message. So this has been deleted, and now we can check whether message 1 is available, and you'll see message 1 while message 2 has been archived. We can now delete message 1 as well. It has been deleted. If we run it again, it should be false. We also get PGMQ metrics for all of our queues. So the queue length, the newest message, the oldest message, the total number of messages that went through the queue, the scrape time, and the queue visibility length. And then we can also get the metrics for a specific queue, which is the same output but filtered for a queue. And now let's look into how this works in Python via our notebook. So let's start up the Jupyter notebooks again. And in here you'll find the PGMQ notebook. So we are using the Tambo PGMQ Python library. This is an official part of the PGMQ repo. And so we are going to import this library as PGMQ. We're going to load our environment variables so that we can connect to Postgres, and we've got our Postgres environment variables here. We can create a connection to PGMQ by using this class and the previous environment variables, and then let's create a queue called notebook, and let's, by the way, check whether this has been created in SQL as well. Let's just open a new terminal window. So let's go to let's list the tables under PGMQ, and as you can see, there is an archive for notebook. There is also a queue for notebook. These are the partitions for the requests queue, but let's go back to our notebook. So now let's send this message. You can use a Python dictionary directly. Let's send it to the notebook queue, and now let's try to purge the queue. The output's 1. If I do it again, it will be 0. And then let's try to read the queue with a visibility timeout of 10. And if the queue is empty, which it is, we'll get none back. If it's not, our message will be printed. So the queue is empty. Let's try again to send a message. And as we can see, we can retrieve that message. If we purge it, we purged one element. This is the ID, this is a count, and the queue is again empty. Finally, let's go into some pros and cons, just a generic comment on our options. So comparing PG search, ParadeDB with Elasticsearch. ParadeDB is ACID compliant, so you've got transactions, integrity, concurrency, and disk storage. Elasticsearch, on the other hand, is eventually consistent, so it's base instead of ACID, which allows for high availability. ParadeDB is based on SQL and it supports joins, and Elasticsearch uses a custom query DSL which doesn't support join operations. ParadeDB is good for combining structured and unstructured data, while Elasticsearch is ideal for advanced search needs that require high throughput. So comparing PG routing and Neo4j, there is no index-free adjacency in PG routing. Instead, it has functions like PGR extract vertices to help improve performance, but only for very specific operations. It has a limited selection of algorithms, so for centralities it supports betweenness and it's experimental. and it supports degree. For pathfinding, it supports Dijkstra and A*, but there is no sampling, random walks, embeddings or clustering. Now looking at PGMQ versus Amazon SQS, which was the inspiration for PGMQ. SQS supports FIFO queues and delayed sending up to 15 minutes only, while on PGMQ there is delayed sending. No out-of-the-box feature exists to guarantee message order. SQS is highly auto-scalable, as is frequent with cloud services, while PGMQ only scales as much as Postgres will allow it, which is not bad at all. SQS provides dead letter queues, but PGMQ does not. And PGMQ is generally higher latency and lower throughput than SQS. So just to clarify, dead letter queues are essentially queues where messages for failed jobs end up at, or if there is some timeout or expiration when a job is running, it will end up at a dead letter queue, and then the software developers should monitor these queues for errors and manually fix and handle those requests that had failed. While I was working on this series, I found out about this service, an open source solution called PIGSTY, which stands for PostgreSQL in great style. So this provides an alternative to AWS RDS. It provides extensible Postgres, reliable infrastructure, observables, scalable, maintainable, composable service. So PIGSTY, they do a good job on marketing, and they provide self-hosting for Postgres, which is kinda interesting. And of course they support every extension you can think of, and they try to obviously sell you this service instead of you having to go through the open source solution of self-hosting. You can just pay them and you'll get all of this without having to handle infrastructure yourself. This sector is moving extremely fast as the open data lakehouse is taking hold of the community. More and more services are focusing on analytical needs based on table formats like Apache Iceberg or Delta Lake. Just in the few weeks it took me to prepare this video series, Tembo refocused to automating engineering tasks with AI workflows. They were focused on Postgres. ParadeDB dropped PG Analytics in favor of centralizing everything on PG Search, kind of like what Elasticsearch does with the Alk stack. And BigQuery is now offering a talk entitled Lakehouse Live, architecting the future of open lakehouses with Google Cloud. So as you can see, everything is moving fast in the data engineering area, with companies failing fast and building even faster. As a final note, here's a bit of advice: don't chase the hype, and this goes for Postgres Maximalism as well. Remember that Facebook was able to hit global scale with a MySQL cluster and memcached before having to switch to HBase to power messages, real-time analytics, monitoring systems, and for a while even the feed generation. So by the time you succeed in your business, you'll be able to hire a team to scale it up. So don't over-optimize, don't prematurely optimize, and instead focus on the product. Next time we'll dive into graph databases, moving away from Postgres for a while, and we'll look into music discovery, diving into KuzuDB, a fairly young graph database that first released in Q4 of 2022. As usual, the unedited research notes for the PostgreSQL Maximalism series can be found at datalabtechtv.com. You can also follow the channel on Blue Sky and join our Discord to receive announcements and discuss topics like data science, data engineering or MLOps. Don't forget to drop a like and subscribe. for all things data.